Hey everybody, welcome back. I want to talk about traffic types. Over a network, there's a lot of different types of traffic that is flowing over the network. Here I'm going to show you what we're going to cover. Network traffic types, addressing, and how devices handle that traffic at various layers. Okay? Traffic types. We got broadcast, multicast, unicast, and anycast. The way that these traffic types are addressed is as follows. Broadcast traffic has a destination MAC address at layer 2 of all. First field is the destination MAC address, usually drawn like this. Ethernet frame, anywhere from about 64 to 1500 bytes, but not really anymore with jumbo and giant frames and jumbo frames, and they get up to 9216 bytes for jumbo framing and things like that. But anyway, this is an Ethernet frame. You have the header, you have the data, which is upper layer protocols, and you have a trailer. So a header, a trailer. In the header is the destination MAC address in the first field, okay? Then you have the source MAC address. Then you have a type field. The VLAN tag would be back here, but that's not in vanilla Ethernet. In a vanilla Ethernet frame, you don't have an 802.1q VLAN tag, okay? We're not going to dive into all the fields in an Ethernet frame right now and all the details of it. We're not going to dive into that. But we are going to talk about that first field, the destination MAC address, okay? If it's all F's, as I just communicated to you, then that is a broadcast frame. All right? Let's change to multicast traffic types. The multicast MAC address will start with 01005E, and then these last hex characters will be a encoded portion of the multicast IP address, not the whole multicast IP address, just I think it's 23 bits of the 32-bit Class D multicast IP address will be coded into those last 6 hex characters of the multicast MAC address. Then, of course, that would be the destination MAC address here in the Ethernet header. It would be the multicast MAC address would be put there. Okay? So looking at unicast MAC addresses, unicast addressing at layer 2, you have, again, a similarly formatted 6-byte MAC address. And in this case, I'm showing you that the X's are what's known as an organizational unique identifier assigned by the IEEE, the Institute for Electrical and Electronic Engineers, and they assign each vendor their own code, okay? So out of all the different vendors of hardware, of NICs, network interface cards, of network interfaces and routers and switches, anything that can generate Ethernet traffic, the IEEE has a list of all the vendors and manufacturers of equipment, and they've assigned a 3-byte OUI vendor code to that vendor. Now that vendor will then take the remaining 3 bytes and it will assign it to a burned-in address that's unique for each one of their interfaces, okay? So that's how a unicast MAC address is. It's kind of an overview of a unicast MAC address. An unknown unicast is the same address as a unicast. We'll talk about unknown unicast in a moment, but suffice it to say that the addressing is no different. Anycast is really a IP technique, and it's really just a special case for unicast, and it's still unicast. So it really has nothing to do with layer 2, but I wanted to mention it there anyway because it's part of our traffic types that we're covering. Okay, traffic types Okay, let's move on to traffic types and addressing of those traffic types in the layer 3 IP header. All right, now we're talking about as traffic moves through a network, it is decapsulated, and as it goes through switches, I'm losing ink on my marker. As it goes through, if this was to go into an Ethernet switch that we'll draw with a box with an X, the Ethernet frame is forwarded or filtered through in this format. If this were to connect to a router, this frame could be forwarded to the router, but then the header is trashed, and as it's decapsulated, the trailer is done away with. And what is revealed is this data field. Well, at layer 3, this data field reveals that it was an IP packet all along. Okay, and so in this IP packet, the header is right here in the front, and you have a destination IP address and a source IP address. And so that's what we're talking about right now with addressing at layer 3. The broadcast, there's an all ones broadcast, usually is not forwarded. We'll talk about that later. And then there's a all host broadcast where, if, for instance, in the case of a /24, we know that the network bits are the first 24 bits and the host bits are the last 8 bits of the 32-bit MAC address. If you want a refresher on that, find some of my subnet videos, and I explain a good bit about what host bits are, and what network bits are, and how to know what a broadcast address is for a given subnet. In this case, we're talking about a /24. The all host subnet broadcast is when you set the host bits to binary ones, which equals 255, and that's called a subnet all ones broadcast. Okay, and that's what could potentially be in the destination IP address, the destination IP address of this packet. Okay, now multicast traffic type at layer 3 and the addressing related to that is of the Class D address space. There's a lot of different types of Class D address space. There's private, there's source-specific multicast, and so there's a few different kinds there. All right, so that's of the Class D type, starting with 224.0.0.0 up to 239.255.255.255, and so that's your Class D address space. Unicast is really the bulk of the traffic type on our networks today and on the internet at large. Probably 99% of the traffic is Unicast. So you get to know this very well. Of the really big categories of Unicast address space, you have private RFC 1918 address space, which is not routable on the public internet. It's not that it's not possible to route it, it's just that by policy, service providers don't allow it to be routed. Router software will allow it to be routed. It's just that there are ACLs on boundaries between providers and on the internet, and there are routing policies that disallow it to be routable. Okay, so you can use it within your network, but you just can't use it out on the public internet. That's what public address space is for. And so to get public address space, you need to contact your regional internet registry. In North America, that would be the American Registry for Internet Numbers, ARIN, pronounced Aaron, like myself, like my name. And so that's Unicast address space. Then you have Anycast address space, and it is a special case Unicast, like I mentioned before, but it's still Unicast. So an Anycast IP address is in fact a Unicast IP address. All right. And I'll also mention that Unicast address space can be acquired by your upstream provider, not just the regional internet registry. That's provider agnostic address space, or provider neutral. But if you link to an upstream provider, you can request IP space from them. They might give you a little bit, but they'll probably charge you for a lot more. Let's talk about traffic types and the way devices in a network handle that traffic type. Okay? So when I say devices, I mean switches and routers, and broadcasts are flooded. Okay? They're flooded except where they are received, except on the port they are received. And what I mean by that is, first of all, I'll remind you that we're at layer 2, we're talking about Ethernet, and at layer 2, for the broadcast traffic type, we're talking about an all Fs hex MAC address in the destination field of an Ethernet frame. Okay? So if this is our network and this PC sends out an Ethernet frame, and in the destination field, it's kind of funny because every time we draw Ethernet frames, a lot of times we draw the header over here, even though the traffic is flowing that way. So, I'll just go with that. Let's just say the header is over here, and we have the Bcast destination MAC in the header. When it arrives at this Ethernet switch, it will get forwarded out every port. So you know what? I'm going to expound on this diagram just a little bit to show another PC here. Okay? So as this Ethernet frame with a broadcast MAC address arrives at this switch, the frame will be sent out this port, and it will be sent out this port. Okay? It will not be sent back out the port that it was received on. That's why I mentioned it floods it except where received. The definition of flooding is send it out every port on the switch that actually has something connected to it. And by the way, whatever is connected has to be enabled. It has to be powered on. I mean, if you had this computer turned off, there's not a legitimate link there. There's no electrical signal there unless you have wake on LAN. But we're not talking about we're not talking about a NIC that's sitting there and is actually has carrier detect on it and is actually causing the switched port to be green. If it's powered off and the port is dark and is not sensing any link, then the frame's not forwarded out of it. Okay, so the link has to be active, the port has to be up, and I'm also going to caveat this with, we're talking about a single VLAN scenario. Okay, so we're not going to get into a lot of details about VLANs, but what I'm talking about is true about bridge domains. It's true about VLANs. Bridge domains, VLANs, same thing, same concept. It's an administratively defined broadcast domain. You know what I just did? I just mentioned a few things there. A Bcast domain is the domain. The word domain is just a general term, but it means, some kind of the confines of something. And so a domain, a broadcast domain, is a domain that is defined by how far a broadcast can reach. Well, a VLAN scopes broadcasts. A bridge domain scopes broadcasts. They're both administratively defined broadcast domains. Okay, back in the day, before VLANs, a repeater hub or a switch was a broadcast domain, every port on it. When the invention of VLANs came out, you could then define what port was on what VLAN, and so then a port on a VLAN that received a broadcast from a PC, that switch would only flood that port out the other ports that were in that same VLAN. So this is true today. So all that, I just wanted to give you that background. All that to say, this example of how far a broadcast can be flooded is all about the scope of a VLAN. Okay, so we're just talking about a single VLAN scenario here. And as I mentioned, this layer 2 broadcast addressed Ethernet frame is flooded out every port except the one it's received on. When it arrives at the router, we're going to talk about how that handles this traffic type in a moment. Well, you know what? No, I'm going to talk about it right now because we're talking about layer 2 broadcasts. And so you need to know routing 101, basic routing knowledge. You must know a router is always and forever a broadcast boundary. A router is always and forever a broadcast boundary. This Ethernet broadcast will never cross that router's forwarding plane. Okay? I'm not talking about if this router was configured with MPLS layer 2 VPNs, or it was configured for a bridge domain between one port and another. It was doing integrated routing and bridging. Concurrent routing and bridging was what it used to be called. I'm not talking about that. I'm talking about basic routing, and that's what you need to understand. Basic routing, a router that's got this layer 3 interface and this layer 3 interface separated into two separate subnets. This router will always and forever stop broadcast from coming from either one of the sides of these layer 2 domains. That's a layer 2 domain. This is a layer 2 domain. That router will stop those broadcasts, okay? You need to know that. Now, you might say, well, what if this is a multi-layer switch? Again, I'm not talking about if this switch has the possibility of a routing function in it, or even if it actually is routing. What I'm talking about is if this device has these 3 ports in the same VLAN, this is what's going to happen. If this device has a routing function in it, but it's routing for other VLANs, that's irrelevant to the topic of what happens in this VLAN that we're discussing. So let's talk about multicast. Multicast MAC addresses. Okay, so they flood except where they're received unless multicast and IGMP is enabled. All right, so what we're talking about is, again, in the scenario of a PC right here sending a multicast Ethernet frame. If this PC sends an Ethernet frame that has a 01005E, and there's X's over here that represent the Class D multicast address. But if this destination MAC and this Ethernet frame is a multicast MAC address, and this switch is not enabled with Internet Group Messaging Protocol, back in the day it was CGMP, Cisco proprietary. But if this layer 2 environment is not multicast enabled, this is treated like a broadcast. Okay? Everything we just talked about with broadcast is true about how this is going to handle this multicast frame. Again, if this layer 2 environment is not multicast aware. If it is multicast aware, then it will be efficiently forwarded based on where the multicast router is and some other things that we're not going to get into right now regarding multicast. So there is some efficient handling of multicast traffic in a layer 2 environment when multicast routing protocols are enabled. Otherwise, it's flooded, just like a broadcast, okay? Let's talk about Unicast at layer 2 now and how devices handle layer 2 Unicast Ethernet frames. First of all, an unknown Unicast, I think I may have mentioned this before, but if not, I'm going to remind you that an unknown Unicast MAC address is the same MAC address as a Unicast. It's just that it is unknown at the moment. Okay? And so what do we mean by unknown at the moment? It's unknown from the perspective of the Ethernet switch that is receiving it. So an unknown MAC address, we really need to understand what the word unknown means. Because an unknown Unicast MAC address is the same as a Unicast MAC address. It could be literally the same frame. And it could literally be the same frame just a split second before. So then what's this deal with known Unicast and unknown Unicast? I'll tell you. It's unknown inside the bridging table or the MAC address table of this layer 2 device, of this switch. If this switch has no knowledge of this destination MAC address inside, remember we're talking about the Ethernet frame that's coming from this PC in this direction. And we already know that Unicast MAC addresses are assigned by the IEEE to vendors and all that. We know we know what a Unicast MAC address looks like. But as this frame arrives into this switch, if this switch has no knowledge of it, and we'll talk about how it learns it, but if it has no knowledge of it, it's treated the same as a broadcast and a multicast if there's no multicast awareness. It's flooded. So the word flooded can pertain to broadcast. It can pertain to multicast in an environment that's not multicast enabled. And again, the word flooded can also pertain to unknown unicast. Now, that brings me to a term, BUM. B-U-M. Broadcast unknown unicast, not that doesn't stand for unicast. It stands for unknown unicast. BUM traffic is broadcast unknown unicast and multicast. And the reason there's a term for it is because BUM traffic is all flooded. So I just told you bit by bit what happens with a lot of these things, but I could have grouped them all and just said, hey, BUM traffic is flooded. So this is what I've been doing is I keep saying that broadcast is handled this way, it's flooded. Multicast in an unaware MCAST enabled network is flooded, and unknown unicast is flooded. Well, that's what BUM is. BUM traffic is flooded. Broadcast, unknown unicast, and multicast. All right. So just real quick, as I make a note in unicast, known unicast is efficiently forwarded. In other words, it's not flooded. Okay? So what makes a unicast MAC address become known? Well, it's as simple as this. When a Ethernet frame is sent from a PC into the network, the source, this next field, SRC, the source MAC, I'm just abbreviating, the sourced MAC is learned by this switch as it arrives at that port. It's called, just kind of like a passive listening or a snooping of sorts. You don't turn it on. All sorts do it, all switches, all layer 2 devices, all VLANs, all bridge domains do this by default. It's called MAC learning. You can disable MAC learning in some service provider equipment or various gear. But by default, a standard switch has MAC learning. Source MAC snooping is enabled. Well, it's because this is how switches do their thing. This is the power of an Ethernet switch. It's the efficiency of an Ethernet switch. And so when this Ethernet frame comes in, it might be unknown in the destination field and it might get flooded. But I'm going to tell you one thing. As it got flooded, it got learned. The source got learned. Not the destination, the source. So now this PC's burned in MAC address is known in this bridge table. If I had to blow this up and draw the MAC forwarding table, otherwise known as a content addressable memory CAM table, sometimes referred to as CAM table. Easy to remember because CAM flipped backwards spells MAC. It's like a MAC, and it contains the MAC table. So if this was port number 1 and this was port number 2 and this was port number 3, the source MAC address, the MAC address of this PC is in fact the MAC address in the source field of this Ethernet frame. It then gets put in the CAM table on port number 1 and blah, 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 that source MAC address is put there. So let's just say, for instance, this frame gets flooded. And let's say this frame was intended for this PC. Well, the router gets it. We know the router stops it because we know that a router forms a boundary Yeah, let's just, it's not a bit, we're talking about Unicast at the moment. So the router is not stopping Unicast because it's a broadcast boundary. The router in this case is stopping the Unicast because it was intended for this PC and the router should know it doesn't need to take further action. We'll talk about what routers do later, but it was intended for this PC. So because of flooding dynamics, it ends up at the router, but it also ends up where it's supposed to go. This PC eventually responds. This switch learns the whereabouts of the source of this Ethernet frame. Here's the destination. Here's the source. Snooping causes the switch to learn about this PC's burned-in address. So now we can say the switch builds a MAC address for PC number 2, or this second PC down here. But the way that it's forwarded is efficiently forwarded across the forwarding plane of this switch, because previously this MAC address was learned when this frame came this way. You see what's going on there? So this is the dynamics, the auto learning of an Ethernet switch, and what happens before, during, and after MAC learning takes place. We are now over to Anycast. We already know that an Anycast is really a Unicast, so it's forwarded in much the same way that we already talked about with Unicast. Traffic types and how they are handled at layer 3. So the way traffic types are handled at layer 3, this is the job of a router. Okay? So we're talking about the traffic types as they have been received at this router here. We draw routers with a circle and an X in them. And so that's what this is here. This is our router, a circle with an X. Okay? And broadcast. So broadcasts, as I mentioned before, are usually filtered and not flooded through a router. There was an attack vector back in the day, and a lot of what are known as directed subnet broadcasts have been by default disabled in pretty much all routers these days. Okay, so broadcasts are not forwarded by routers. Okay, they're not forwarded. So that takes care of broadcast. Now multicast, as I have mentioned here, is also not forwarded, doesn't forward unless multicast has been enabled. Okay, so what we mean by that is a router must be running a multicast routing protocol. You usually have to globally enable multicast routing in Cisco products, and then you need to have multicast routes that are learned, usually by some variant of PIM, Protocol Independent Multicast. And then there needs to be a multicast source application. There needs to be multicast receiver or listener applications on the end devices. And so in a non-multicast enabled network, like broadcast, multicast isn't forwarded either. Okay? Brings us to Unicast. Unicast, again, the bulk of the traffic you're going to find on your network and the internet at large. Unicast is forwarded using routes that are either directly connected routes, static routes, or dynamic routes. The routing table is what's known as the routing information base, the RIB. If I could draw a thing in here, you'd have the routing information base, otherwise known as the route table, TBL, and you'd have entries in your routing table. Right off the bat, this router has two routes that are known to it. If this network is configured and it's ready to go, then this is a 3 network device network. I'm not talking about the PCs, I'm talking about 3 devices that do forwarding. You have 2 switches and a router, which means this is a pretty simple network with a subnet over here and a subnet over here. Subnet A with some kind of a slash mask, some kind of a mask. This is subnet B with some kind of a mask. And so with this router not having any other neighboring routers, there's no reason to run a dynamic routing protocol. Even if there was a neighboring router, that's a pretty simple network. You could run static routes between 2 routers and be fine if that was all you had to deal with. If you were going to grow that network, you want to set it up for the future and start running a dynamic routing protocol. But in a network like this, no need for a dynamic routing protocol, and there's 2 subnets. You see them. Well, in the routing table, you're only going to have 2 entries. You're going to have a route for subnet A and a route for subnet B, and whatever those masks are, I'm putting question marks, and it's going to tell you what port it's on. Let's say this is on 00 and this is on 01. It's going to tell you 0001. I'll put a D there, DIR, directly connected or connected. And so that's how these routes were learned. They were learned because you configured an IP address on both of these interfaces that's a non-overlapping subnet, correctly subnetted, and the route table has 2 entries, and they're called directly connected routes. And so Unicast traffic would be forwarded based on those directly connected routes. If an Ethernet frame was to be sent through here, when it gets to here, it gets decapsulated, processed up the protocol stack to layer 3. The router looks at the destination IP address. If it is in fact this subnet over here, it forwards it. Okay? And so this is how Unicast routing works. Anycast, as I've mentioned before, is a special case of Unicast, but it's still Unicast. So this concludes this video on traffic types. I really felt compelled to put this video together. It's really valuable to know how devices handle traffic, what the address types are based on those traffic types, and I hope this is helpful to you.